So good afternoon. This video is to introduce you to the greenhouse effect in detail, not like you've ever heard before, possibly. So again, if you are unfamiliar with what the greenhouse effect is, it's the phenomenon where the gases in our atmosphere are causing the Earth to heat up. And that's pretty much everybody's basic understanding of the greenhouse effect. However, in this video and the next video, you're going to learn the science behind why the greenhouse effect warms up our planet. There are three systems that we must talk about in order to fully understand the greenhouse effect. In this video, the two systems we're going to look at are the sun and the earth. The next video, we're going to concentrate on the atmosphere. So we're going to look at what the sun is doing first, and then we're going to look at what the earth is doing next and discuss what we mean by a black body object. So first, the sun is definitely emitting a huge amount of power on a daily basis. And how we measure the power that is actually being emitted from the sun is we measure its intensity. And intensity is defined as the power per area. And so remember, power is joules per second. Area is going to be in meters squared. And that means that the units for intensity turn into watts per meter squared. We actually have a literature value to describe the power emitted from the sun, and that literature value is 3.6 times 10 to the 26 watts, or 3.6 times 10 to the 26 joules per second. So we can actually calculate the power and the intensity of the energy leaving the sun and coming to the earth, because we know how far away Earth is from the sun. If you look at this diagram down below here, we are 1.5 times 10 to the 11th meters away from the sun. It's another literature value. And if we think about the distance we are away from the sun as the radius of a sphere, we can calculate the actual surface area of that sphere using an equation you've probably seen in geometry. Surface area of a sphere is found by multiplying 4 times pi times the radius squared. So if we take the literature value of our distance away from the sun, and we know that the power being emitted from the sun is 3.6 times 10 to the 26 watts, we can absolutely calculate the intensity of the energy reaching our planet. So let's do that now. If I take a look here and remind myself of the equation, intensity is power over area. And in this case, it's going to be power over 4 pi r squared. I know the power is 3.6 times 10 to the 26 watts. I know 4 pi and my radius is 1.5 times 10 to the 11th. And when I solve this out, the intensity of the energy that leaves the sun and makes it to the earth is going to be, no sig figs calculated here, 1,273 watts per meter squared. Now you could tell that the closer we are to the sun, the greater the intensity would be. The further away we are from the sun, the less the intensity from the sun would be. So this is the amount of power per meter squared that is actually hitting our planet from the sun per second. So what type of energy is leaving the sun and actually hitting our planet? Electromagnetic energy. So electromagnetic energy is also referred to as electromagnetic radiation. It's defined as energy that is emitted by a passing of photons that have particular wavelengths and frequencies. Photons are incredible little particles that are a cross between something that is matter and then that is something that is pure energy. How photons are created, and we're going to get a little bit into chemistry here. Photons are the most elementary particle of light energy, and we can think of photons as little tiny traveling waves that, as Einstein discovered, have mass, even though it's infinitesimally small. And they are also thought of as energy. And there are 1, 2, 3, 4, 5, 6, 7 different types of photons. And each of those types of photons has a corresponding wavelength. So radio waves are the longest photons that leave an object, whereas gamma rays have the shortest wavelength of any photon leaving an atom. And I'm going to show you how these photons are created by having you look at an animation that you're probably going to play around with in chemistry. So here's how photons of energy are created. Here we have what we call the Bohr's model of an atom. And you might have heard in physical science an atom has protons and neutrons that live in the nucleus. There they are. And then there are electrons that live in different energy levels around the nucleus inside of an atom. You're going to get into a lot more detail about this next year. So each ring represents an energy level in this very simplistic model of an atom. And what I'm going to do is I'm going to take this electron and I'm going to make it jump between energy levels. As I do that, pay attention to what's happening on the absorption spectrum and or the emission spectrum. So the first one I'm going to do is jump from energy level 1 to energy level 2. Watch carefully. You saw that the atom absorbed a photon of energy with a wavelength of 121 nanometers. Well, that wavelength corresponds to a photon that falls in the ultraviolet region of the electromagnetic spectrum. Now, if I jump back down to the first energy level, watch what happens in the emission spectrum. That photon with the same wavelength has now left the atom as the electron goes from the second energy level to the first. And if I jump from 1 to 4, I still have a UV photon entering the atom. And if I go 4 down to 1, I will see a photon with wavelength 101 leave that particular atom. And you can play around with this. If I go from 3 down to 2, notice I'll get infrared. I can also play around with this simulation and change my radii. And if I change the radii of the energy levels, I can find photons that are in the visible light spectrum, which is how we get colors of light. So this is how photons or electromagnetic energy is created. It's the bouncing of those electrons between energy levels. So again, here's my electromagnetic spectrum, and you will see that we created photons of energy in the ultraviolet range, which were 121-ish nanometers, which if we translated that to meters, it'd be 10 to the negative 10th meters. Visible light has a wavelength of 400 to 700 nanometers. So if a photon falls in that range in terms of wavelength, we'll be able to see that particular electromagnetic energy. And it's the only electromagnetic energy we're able to see. If we increase the wavelength to 10 to the negative fifth meters. I get infrared and even longer microwaves, even longer than that, radio waves. So this is how electromagnetic energy is created. Next thing we're going to look at is how this electromagnetic energy heats up our planet. So we've talked about what the sun is doing. Let's talk now about what's happening to the Earth when this energy encounters our planet. There are two ways in which our Earth heats up. And this is way number one. The Earth is going to reflect some of that electromagnetic radiation that comes from the sun onto objects on the Earth's surface. So my electromagnetic energy comes in and bounces off like that. This arrow didn't need to be there. And that reflection causes objects on the Earth's surface to heat up. That is the first way we have an increase in temperature on our planet. But the second way is the most important way when we're talking about greenhouse gases and we're talking about the greenhouse effect. Way number two is that the Earth absorbs some of this electromagnetic energy that comes from the sun and then emits some of that energy in the form of infrared radiation and microwave radiation. And this is because the Earth, as with any object, has what we call black body tendencies. So what I'm going to diagram here is that the energy from the sun will actually go into the Earth, and then what happens next is that energy will transform and then radiate out into the surroundings from inside of the Earth's core there. And this is due once again to the nature of the Earth being a black body emitter. So what is a black body? A black body is any object that can absorb all electromagnetic radiation that encounters and reflects none of this. None of the energy would bounce back off, but then emits that same amount of electromagnetic energy back out into the surroundings. So a perfect black body is exactly as the name implies, something that is as black as possible. So we really have no pure black body emitters. Coal comes close because coal is really, really black. And the reason why coal is such a great black body emitter is because black, the color black, can absorb all forms of electromagnetic radiation. The color white can emit all forms of electromagnetic radiation. So that's how we get the phrase white hot. As the temperature of that black body increases, the intensity of that black body also increases. So what happens is that as you increase the temperature of an object, such as a black body, the amount of power that is emitted by that object is also going to increase. At this point in time, it's a great point to stop the video, go back to your Schoology page, and I've put a link up to a video showing a demonstration with infrared vision of a black body object. So hopefully what you saw in that infrared video was that when you had the infrared camera on, you could not see the piece of steel rod in the infrared because the temperature wasn't high enough. As soon as the professor started to increase the temperature of that steel rod, you actually saw the steel rod begin to glow. And it began to glow because the amount of energy, or the type of energy that was being emitted from that steel rod, shifted from a wavelength that we could not see into visible light. So it took an increase in temperature to shorten the wavelength in order to see that glow. So as you saw in that video, as temperature increases, the wavelength of the photons emitted will shorten. And if you shorten them into the range of 400 to 700 nanometers, you will end up seeing a glow just like you saw in the steel rod. If you decrease the temperature of a black body object, the wavelengths of photons that are being emitted will increase. So that means you're going to shift into a range of the electromagnetic spectrum that we can, again, not see, just like we as people are black body objects in some respect, but the energy we are emitting is infrared energy. That's why you can see the energy emitted on the infrared spectrum when you use the camera. This is called a Wien's diagram. And what the Wien's diagram does is it shows the type of electromagnetic radiation that is most predominant for a black body object. So this is a Wien's diagram for the sun, hence solar, and terrestrial means the planet Earth. What you look for in a Wien's displacement diagram is the highest peak. Highest peak for the sun is right here, and if you notice that the highest peak with the highest intensity of electromagnetic radiation happens when the wavelength is in the visible light spectrum. That's why we can see the sun and see the energy being emitted from the sun, because the wavelengths that are being emitted are not only visible light, but any other sort of electromagnetic energy as well. But what we see is that visible light. Here's the Earth over here. The Earth will be a black body. It's not as good of a black body as the sun, but nonetheless, it has black body characteristics. The intensity of the wavelengths at 10 micrometers fall in the infrared range and has the highest intensity. So that means that the amount of energy, or the type of energy being emitted from the planet Earth, falls in the infrared spectrum. What you're going to do is you are going to play with a PhET animation that you are going to look at the sun, the Earth, an oven, and a light bulb, and look at the black body tendencies of those four objects. You are going to find that simulation attached to Schoology along with the worksheet. And the worksheet, I believe I let you know that the worksheet gets completed into your notebook.